Uh, okay, so for the second talk of the day, we have Hassaan Saleem talking about non-supersymmetric closed strings on AdS4. Go ahead.
Okay, thank you, first of all, for to the organizers for inviting me to this talk. So I'm going to talk about non-supersymmetric closed strings on AdS4, and it's based on this work that I did with Ivano Bazil and my advisor, Daniel Robbins. So first of all, let's talk a bit about non-supersymmetric strings. So there are 10-dimensional string theories that don't have tachyons, and they are non-supersymmetric string theories. So one of them is called the heterotic O16 cross O16 theory, and the other two are open string theories. So I'm going to talk about the first, string theory, which is non-supersymmetric, 10-dimensional, and without tachyons. Now, you do know that in non-supersymmetric strings, we do have loop corrections, to the cosmological constant. So one question that you can ask is that can you uplift AdS space-time to de Sitter space-time by these loop corrections? And there's one more question that one should ask, and that question is that are non-supersymmetric backgrounds stable, or at least metastable? But there are two kinds of stability that you can talk about. One stability is perturbative stability, and that means that all the mass squares that you get, if you are talking about Minkowski spacetime, then they should be non-negative. But if you're talking about AdS spacetime, then all the mass squares should be above this bound called the BF bound, and it depends on what kind of particle you're talking about. The other kind of stability is non-perturbative stability that Vincent just talked about. And that particular stability is against non-perturbative processes, for example, brain nucleation. So I'm going to talk about both kind of stabilities in this talk. So some backgrounds for the heterotic O16 cross O16 theory have been studied. For example, this background has been studied by this group, and then this Grania and SETI group. And this other background has been studied by myself and my advisor. So what happens in these backgrounds is that the uplift to de Sitter doesn't happen, which is not surprising, to be honest. The second thing that happens is that the perturbative stability of scalars is checked, and it turns out that all the scalars are above the BF bound. But vectors and tensors are not checked in these backgrounds. And the last thing is that the non-perturbative stability is not checked. Why? Because both of these backgrounds have some torus. So this first background has S1, which is a one-dimensional torus. And the second background has T4. I should have written T4 here. So it's AdS3 cross S3 cross T4. And you can have tunneling in torus moduli space that makes the analysis quite hard to understand. So, sorry. So we're going to discuss this background, AdS4 cross S3 cross S3. And one of the main motivations is that this background doesn't have any torus moduli. So non-perturbative stability becomes easier to understand. The second thing that this background has is that it has inverse scale separation, which is an interesting feature. So what turns out is that one of the spheres becomes bigger than the AdS4 component. So we're going to study this background in this talk. So the first question is uplift to de Sitter. So if you start with the 10-dimensional action of heterotic O16 cross O16 theory, the bosonic part, and you study the AdS4 cross S3 cross S3 solution and write the metric like this, where these chi and chi tilde are volume moduli of the two spheres, then it turns out that the potential is given like this. And you can write down the derivative of this potential. And it turns out that the equations that you get from the derivatives being zero are inconsistent, which means that the tree level solution doesn't exist. So you have to add one loop correction in order to get some solution. So the one loop correction comes from the integral of the partition function over the fundamental domain. And the expression looks like this. I mean, I'm not going to go through the derivation, of course, but this is the expression. If you add this, one loop correction to the potential, then you can calculate the derivatives and get the equations. But the equations are hard to solve analytically. So we solve them numerically and we can plot the solutions. So one solution that we can plot is the radius of the sphere. So L and L tilde are the radii of the two spheres. And N and N tilde are and H3 fluxes on the two spheres. So you can plot L versus N, and you can see that if the flux on the corresponding sphere increases, then the radius increases. But if the flux on the other sphere increases, then the sphere radius goes to a constant value. And this happens with the other sphere as well. So here, the flux on the second sphere is increasing, therefore the radius is increasing. And here, the flux on the first sphere is increasing, so the radius of the second sphere goes to a constant value. The second thing that happens is that the G string goes to a constant value if either of the fluxes goes to a small value, right? It seems to be the case that it's diverging, but it's not diverging. Actually, it goes to a constant value. So G string remains small, which is similar to other constructions that I discussed before. And one of the most interesting things that answers the question that we are discussing here is that the V minimum, the minimum of the potential, never becomes positive, which means that you never get a de Sitter solution. So the de Sitter uplift doesn't happen. You can see that the minimum of the potential becomes quite close to being zero as as either of the flux increases, but it never becomes positive. So the de Sitter uplift doesn't happen. And one last thing is that the AdS scale, no matter what scale flux is increasing, it goes to a constant value. So you can see that suppose that if n increases without bound, then as I showed you earlier, then this sphere radius increases without bound, which means that no matter what flux you choose and you increase it without bound, one of the spheres is going to become much bigger than the AdS scale. Yes, the AdS scale, which means that you have inverse scale separation. Okay, so the first question has been addressed, that the de Sitter uplift is not going to happen. So the second question is about stability. So let's talk about stability analysis. So again, let's start from the one loop corrected action for this 10-dimensional string. And I'm going to use lambda for this one loop correction. So it's not cosmological constant. It's a weird choice of notation, but this is what we are using. So we can study this solution, the AdS4 cross S3 cross S3, with phi being 0, right? So if you have this, ansatz, then you can write down the Ricci tensors where the cross terms are 0, of course, and the H3 flux is on the two spheres. So there is no H3 flux on the AdS4 part, of course. And if you use equations of motion, then it turns out that these curly L's that are used to define H3 are related to the sphere radii by these equations. And this lambda is the one loop correction, as I told you earlier. Now we can introduce perturbations. So introduce perturbations to the metric, to the B field, and the dilaton. And you can see that I'm using mu and nu for AdS part, A and B for the first sphere, and I and J for the second sphere. Now I have, broken down the perturbation in the metric in two parts. One part is called H mu nu, which is the traceless part, and the other part is the trace part. And the same goes for the first sphere and the second sphere here. For the cross terms, the traceless part is not a thing, so I haven't broken that down. Okay. Now we have to, write down the equations of motion, but we also have to decompose the equations of motion into spherical harmonics. So since we have two spheres, two S3s, we can break down all the fields in terms of the spherical harmonics on the two spheres, right? So that will give us very ugly expressions. So of course, I'm not going to write down the expressions, but it gives you all the equations of motions in terms of spherical harmonics. But I can show you some examples that how fields decompose in spherical harmonics. So the spherical harmonics that I'm going to use, there are scalar spherical harmonics, vector spherical harmonics, and tensor spherical harmonics. And they come with these superscripts where L starts from 2 if you have a tensor spherical harmonic, L starts from 1 where if you have a vector spherical harmonic, and L starts from 0 if you have a scalar spherical harmonic. So for example, if you have a scalar field, it just decomposes like this. And if you have a field where one component is on the AdS component and the other component is on the first sphere, then you have a simple expression like this. And then you can have these kind of examples where two components are on the first sphere. Then you have all these terms. And the most ugly thing is when you have two indices, and each index is on a single sphere. So for here, I'm showing you a field which has first index on the first sphere and second index on the second sphere. Then you have this ugly expansion. So you can do all of these expansions and write all the equations of motion in terms of these decomposed fields, and you will get the decomposed equations of motion. But before I do that, we have to impose the gauge conditions, of course. So we impose these kind of gauge conditions where if you have any field that has one index on the first sphere, then if you contract that with the corresponding covariant derivative, that should be 0. So it's Lorentz-like gauge conditions. Now, it turns out that these gauge conditions they do fix the gauge for all the fields that have L and L tilde greater than 2. But if L and L tilde are equal to 0 or 1, then there may be some residual gauge transformation. So you have to treat these cases with caution. So if I tie everything up, it turns out that you have 6 different kind of sectors These are the 6 different kind of sectors that can come from different, decompositions of the spherical harmonics. And in each sector, you have to, be careful about if L or n L tilde is equal to 0 and 1. So for example, if I take this sector, L0, L0, it turns out that there are 9 subcases that you have to go through. So if I write down all the subcases for all the sectors, it turns out that there are 31 different kind of sectors that you have to go through. Now, of course, I'm not going to go through all the sectors because not all of them are interesting. Some of them are boring. So let me just show you the boring ones first. So these sectors, so these 4 sectors, so here I had 6 different kind of sectors. 4 of these sectors are safe, which means that all of the fields that exist in these sectors have non-negative masses. So it means that there is no chance that any of these is going to violate the BF bound, right? This sector has scalars only, and it turns out that none of the fields here violate the BF bound, although the fields here don't have non-negative mass squares, but they don't violate the BF bound at least. So it means that there is only one sector which is interesting, and it's this one, right? So let's study this sector. So if you take this sector, there are different equations that appear in this sector, but one equation is interesting. And if I take you back, I can show you that when I introduce the perturbations, the cross metric term between the two spheres was called W, and the cross B field term between the two spheres was called P. So the equations for these two fields are interesting. So if I write down the equations for these two fields, W and P, it turns out that you have a mass matrix like this, and if you calculate the eigenvalues of this mass matrix, you get something like this. Now it depends on L and L tilde and this sign, right? So if you choose L and L tilde both equal to 1, right, and you choose this sign such that this sign so you can see that when I introduced this sector, I had this prime on this sign. It just means that this sign is independent of this sign, right? This double prime means that this sign is independent of this sign and this sign, right? So if I choose L and L tilde equal to 1 and choose this sign as negative of the first sign, then it turns out that you have a mode that violates the BF bound. And I have plotted this mode, against the logarithm of the flux ratio. And you can see that this BF bound violation happens when the logarithm of the flux ratio is almost 0, right? Which means that the fluxes are equal to each other. Now you can see that this violation happens when L and L tilde are both equal to 1, which means that if you replace one of the S3s by RP3, then this mode is removed because RP3 will remove all the odd L's, right? So this is the only BF bound violation that we have found, but it seems to be the case that this can be removed if you replace one of the S3s by RP3. Okay, now let's talk about non-perturbative stability. So as Vincent talked about, the process that we are going to discuss here, non-perturbative stability is checked against brane nucleation processes. So, as we know that branes, so if you have, a brane nucleation and the brain expands, it reduces the flux inside the brain, right? So according to that process, what happens is that in this context is that you have an NS5 brane that acts as a domain wall in AdS4. Now, since we have S3 cross S3, what's going to happen is that this NS5 brane is going to wrap a 3 cycle on S3 cross S3. And in the AdS4 component, it's going to have, a 2-dimensional part, which is like a bubble, right? So it can wrap any cycle in S3 cross S3. And, that cycle is written like this, with some integer A and B, non-negative integer A and B. Okay. Now, if we define beta as the, ratio between charge and tension, then for the decay to happen, as Vincent talked about, beta should be bigger than 1 because the charge should be bigger than tension. If tension is bigger than charge, then the bubble is not going to expand, right? And for the semi-classical approximation to hold, beta should be of order 1. If beta is much, much bigger than 1, then the semi-classical approximation breaks down. So we need to ensure these two things. Now we can calculate beta for our case. We will need to calculate charge and tension and calculate their ratio. So I'm going to skip all of the intervening algebra, and I'm going to give you the result. So beta looks like this, and these weird things are just ratios. So this xi is the ratio between the radii of the two spheres. This zeta is the ratio between A and B are the integers that I introduced here for the 3 cycle that NS5 brane wraps. And mu is the ratio of the fluxes, but it's not an independent ratio because it depends on this, radii ratio through this expression. So you can write down beta in terms of these two ratios only, xi and zeta. Now, we want to figure out the process that has the largest value for beta, which means that the decay happens most quickly. So we need to maximize beta for a given value of xi, right? Which means that we need to find the value of zeta for a given value of psi that maximizes beta. So if we do that, it turns out that the maximum value of beta depends on if xi is bigger than 1 or smaller than 1. So if xi is bigger than 1 or equal to 1, it turns out to be this. And if it's smaller than 1, it turns out to be this. Now, one can plot this maximum beta against xi. But you can see that if both fluxes are equal to each other, so you can see that if both fluxes are equal to each other, then mu is 1. And mu is 1 means that xi is also 1. Xi being 1 means that the two radii are equal, which makes sense. So if the two fluxes are equal to each other, then beta is square root of 5 over 3, which is bigger than 1, and it's of the order 1. So the semi-classical approximation doesn't break down here, and the decay does happen. And if you plot beta max, against xi, you will get some graph. But for aesthetic purposes, we're going to plot it against, the flux ratio. But that's the same as, the ratio for the radii. So if you plot it, you get something like this. So what happens here is, you can see that I have plotted it against, the tangent inverse of the flux ratio because that gives a nicer graph. But the important point here is that the value of beta max is minimum where the two fluxes are equal to each other, because at that point, tangent inverse of the flux ratio would be equal to 0.707, which is 1 over square root of 2, right? So at this point, beta max is equal to, square root of 5 over 3, which is bigger than 1, and it's of the order 1. So it means that there is no flux configuration that is totally stable, which is not surprising, but it seems to be the case that this is at least metastable. But if one flux is much bigger than the other one, then the non-perturbative decay happens very, very quickly. And it brings you to, a configuration where the two fluxes are equal to each other. But the interesting part is that where the non-perturbative stability is the highest is where we found the BF bound violation. So the BF bound violation happened where the two fluxes are equal to each other. But it turns out that, as I mentioned before, that you can remove that if if you replace one of the S3s by an RP3. So if you can do that, then it seems to be the case that you won't have any non-perturbative instability, but you will have some non-perturbative instability. But at least you see, it seems to be the case that you have a metastable, configuration here. Okay. Now, there are some future directions that I want to discuss here. So one thing is that how about non-perturbative analysis with torus moduli like T4 or S1 or even K3? No, it's not a torus modulus, but still K3 moduli. Now, we do know that tachyons are removed if one S3 is replaced by RP3. So what about the holographic picture? Can you have a holographic picture of this background if one of the S3s is replaced by RP3? Because for the holographic picture to exist, you have to get rid of tachyons. And the last thing that, and this is a very interesting question, can we make general statement about the stability of AdS across anything backgrounds of non-supersymmetric theories? And when I say stability, I mean perturbative stability and non-perturbative stability. So these are some of the questions that I look forward to work on in the future. So thank you.
Thank you, Hassaan. Are there questions for Hassaan? Okay, I don't see any hands for now. Maybe I can ask you a quick question.
Sure.
When you were talking about the perturbative stability, and you said that there's only one mode that could become tachyonic, but that could be removed by replacing the S3 by the RP3.
Yes.
But I think you always phrase it as, if we can do this, then it's fine. Is it not clear that this is okay to do, or what did you mean exactly?
I think it's not hard. So the only consequence of replacing one S3 by RP3 that I am aware of is that it will change the volume of S3 and one of the S3s. And the non-perturbative analysis is sensitive to the volumes of S3 because it's dependent on the calibration analysis that Vincent talked about. So I think the only thing that should happen is that if you replace one S3 by RP3, is that the value of beta should be multiplied by some value of some factor of 2 or divided by some factor of 2, but that's it. So it's not hard.
And so this mode that becomes tachyonic, is it a combination of modes from the 2s2 or the 2s3, sorry? Like a specific, it's
So
a specific combination of the two.
it's a specific combination.
Okay, yeah.
Uh,
Yeah.
so that so the mode that I'm referring to that comes from the mixed metric component between the two spheres and the mixed B field component between the two spheres. That's where it
Okay.
comes from. But it only exists if you have L and L tilde equal to 1. And L is the label for spherical harmonic on the first sphere, and L tilde is the label for spherical harmonic on the second sphere. So if suppose that if couldn't be equal to 1, then this mode wouldn't exist. If L tilde couldn't be equal to 1, this mode wouldn't exist. So it means that if you replace either of the S3s by RP3, then this mode is
Okay.
gone.
I see. Thank you.
No
Are
problem.
there other questions for Hassaan? Arthur?
Mm-hmm.
Yes, so thank you for the nice talk. A very, very, very naive question. I mean, RP3 is non-orientable, right?
I'm sorry, I couldn't understand what you're saying.
Is RP3 orientable as a manifold?
I think, wait, I think it is, yeah, wait. I'm not sure about that, but I think it is, yeah.
You're modding out, isn't it? I mean, like RP2 is not orientable, right? Because you're the real projective plane,
Right.
you
Yes,
mod out
that's true.
inversion. And I'm not sure whether you mod out inversion here as well.
No, I think I
I'm just
don't.
asking myself whether there is some maybe
Mhm.
inconsistency, because I mean, if you have string theory, you have some kind of vibration of more structure than you see just in the low and the massless modes. And so, are you sure that this is a consistent background for the string theory?
So, as far as I
Okay,
understand it,
somebody says that it's orientable.
yeah, it's orientable, I think, yeah. The thing is that,
But maybe
so
maybe there are other obstructions, topological obstructions, in the sense that maybe it's not an allowed background for the structure that you have in your theory.
I will be surprised if it's not allowed, but I'm not sure. But I will be surprised if it's not allowed because it's orientable. I mean, the thing is that a lot of in string theory, a lot of backgrounds are kind of forbidden because you don't want to break supersymmetry. But I'm not talking about supersymmetric string theories here. You
No,
can
no, I
put your
understand, but
Mhm.
you agree that with the string theory comes a certain structure.
Yes,
I mean, obviously, any tangent bundle, spin bundle, more stuff. I mean, I'm not an expert in this, but I assume other people are
true,
experts.
true.
Is it certain that this RP3 is a consistent manifold for compactifying that particular
Uh,
string theory?
As far as I understand, I think it is. Because the thing is that this replacement of a sphere by RP3 or RPN is not, it's not unprecedented. So, for example, there was this work by Segnotti and Bazil in which they studied fine-Rubin compactifications of, these non-supersymmetric strings. And they also found, a mode that violated the BF bound. And they did a Z2 orbifold of,
I see.
one of the spheres, and that mode was gone. So it's not unprecedented. So I'll be surprised if it's not allowed, but I don't think it's in forbidden.
Maybe one more question. So then you are claiming, so do you in the end have a stable, I mean, do you see non-perturbative stability still in the end?
Uh, so if you
Because
replace one of the,
you seem to say that you're relaxing to the point where the fluxes are equal, and then what happens then?
so as far as non-perturbative stability is concerned, when the fluxes are equal, it turns out that's the most stable thing as far as non-perturbative stability is concerned. But if you talk about perturbative stability, that's exactly the place where you have BF bound violations. But if you can replace one of the spheres by RP3, then the analysis that we have done shows that there are no modes that violate the BF bound.
Okay. Thank you.
No problem.
Are there any other questions? We have time for one more if anyone wants to ask it. Okay. If not, let's thank Hassaan again for his talk.
Thank you for inviting me.
And we'll come back in 2 weeks with 2 more talks. See you then.
Thanks.